Okay, hello students and welcome to today's Friday happy hour exam 2 review. These are the topics that I'm going to cover, almost everything from chapter 4 and chapter 5. Okay, so let's begin. First of all, I'm going to be graphing exponential functions. So for example, number 1, they want you to graph f of x equals to 2x. So when you're graphing exponential functions, these are the values that we frequently use for x, -2 all the way to 3. So let's draw a little table. So when x is -2, right, that means that I'm going to evaluate the function at -2. So we're going to put -2 for the x's, and the answer will give us 1/4. So when x is -2, my f of x or my y value is 1/4. And then we're going to use -1 for x. So when x is -1, we keep repeating the process. We're going to evaluate the function at -1, which means I'm going to plug in -1 for the x's. This gives us a 1 to the 2 to the first power, which will give us 1/2. So when x is -1, my y is 1/2. When x is 0, right, we're going to evaluate f of 0, which means 2 to the 0 power will give us 1. Anything to the 0 power is always 1. So when x is 0, my y is 1. F of 1 will give us 2. So when x is 1, my y is 2. Now we're going to choose the value of 2 for x. So when x is 2, we evaluate it at x equals 2. It's going to give us 2 squared. The answer is 4. And finally, when x equals 3, right, we evaluate the function at f of 3, which gives us 8, because 2 to the third power is 8. So when x is 3, my y is 8. And here's how the graph looks like. Okay. For example, the -2, right? When x is -2, it's going to be about 1/4. It'll be about right there. When x is -1, it'll be 1/2. When x is 0, it's going to be 1. When x is 1, the y value is 2. When x is 2, the y value is 4. And when x is 3, the y value is 8. So this is my function, or the graph of the function. Now let's graph another one. Right, we do the same table. We're going to choose the same points. But here we're going to go all the way to 4. Okay. So when x is -2, we plug in 2 for the x's on the function. It's going to give us 2 to the -3rd power, which will give us 1/8. So when x is -2, my y value is 1/8. When x is -1, okay, we evaluate the function at x equals -1, so it's going to give us 2 to the second power, to the -2nd power, which will give us 1/4. So when x is -1, my y is 1/4. Let's plug in 0. So we plug in 0 for the x, it's going to give us 2 to the -1. It's going to give us 1/2. So when x is 0, my y is 1/2. Now let's plug in 1. When we evaluate the function at 1, x equals 1, it's going to give us 2 to the 1 minus 1 will give us 2 to the 0 power, and the result will give us 1. So when x is 1, my y is 1. When we evaluate f of 2, it's going to be 2 to the power of 2 minus 1 will give us 2 to the first power, and the result will give us 2. So when x is 2, my y is 2. When x is 3, right, it's going to be 2 to the 3 minus 1 power, which will give us 2 to the second power, is going to give us 4. So when x is 3, my y is 4. And finally, let's plug in 4 for the x. So it'll be 2 to the 4 minus 1 will give us 2 cubed. The answer will give us 8. And the graph, let me go back. I didn't graph this graph here, guys, but this is a horizontal shift. If we notice, all the x values moves 1 unit to the right. So this graph shifts to the right 1 unit. Okay. For example, when right on the regular one, when it was 0, it's going to go up here to 1, 1. You see here it is. When it's 2, right? When it's 2, it's going to go up here to the graph is going to move this way to 1 unit, which will give us 2, 2, and so forth. So if you guys, I mean, if you guys can remember the parent functions and how they shift, all these functions have the same shift. Okay, so this is a horizontal shift. Okay. Now let's see what happens if we have, let's graph one more. G of x equals 2 to a negative x is the same thing as 1 over 2 to the x power by using the negative exponent power rule. This will give us 1/2 to the x power. Let's see what happens when we have a graph like this one. So we're going to choose the same values for x. Okay, so if we do that, right, this will be the results for y. And here's my work. Right, if I plug in -3 for the x, we're going to flip it, right? We use the reciprocal and make it positive. So it's going to give us 8. So when x is -3, my y is 8. And if we repeat the process, right, for the rest of the x values, these will be my results. And the graph, it starts high and it goes low. So for example, if we have -3, it's going to be 8. If we have -2, it's going to be 4. -1 is going to be 2, and 0 is going to be 1. When x is 1, it's going to be 1/2. When x is 2, it's going to be 1/4. You see, that's why we don't use more values more than 3, because eventually the graph is going to get closer and closer and closer. As x gets bigger, the value for y gets closer and closer to 0. So the graph will eventually go something like, like the graph is right there. Okay. Now, this is number 4. Here's how you use like an exponential function in real life. Here's a situation. It says the assets in billions of dollars for Prudential Financial Incorporation can be approximated by the function a of x equals to 315 e to the 0.056x, where x equals 7 corresponds to the year 2007. So it says find the assets for the following years, for the year 2000 and for the year 2012. So here's my solution. If x equals 7 corresponds to the year 2007, then x equals 0 must correspond to the year 2000, and x equals 12 must correspond to the year 2012. So for a part, we're going to evaluate the function at a of 0. Right, so you plug in 0 for the x, it's going to give us 315 e to the 0, and anything to a 0 power will give us 1, so the answer will be 315. But it's in billions, so it will be 315 billion. And for b, we repeat the process, right? But now, here I put here good to know. When x is 0 or t is 0, whatever the y value is your initial value. This will be good for the next slide that I'm going to be showing you, which will be number 5, problem number 5. But for now, let's continue with b part. So for b part, we're going to evaluate the function at a of 12, which means we're going to plug in 12 for the x's. So we can use a calculator, right? And I can put here, guys, make sure that when you, it depends on the calculator that you have. If you have one of the new ones that they read here at the math lab, then you'll be okay. But you have to put the caret for the power, then you have to make sure that it's in parentheses. Okay, because at times students make mistakes because they plug it in like they put 0.056 and then they put parentheses 12 and it's going to be wrong. So make sure that it's like this, okay? The product of 0.056 and 12 for it to be in parentheses. So anyway, if we put that in the calculator, it's going to give us something like 616.8171575. Let's say that we round it out to a nearest tenth, so it'll be something like 616.8 billion. Okay. Now this is number 5. It says here, a deadly virus has affected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. Find the model of the form f of t equals to y naught, b to the t power, with t equals 0 corresponds to the end of the month of January. Then for b part, if the trend continues, about how many people will be infected by the end of the year. So for a part, we have to find the function, right? The exponential function. So we need to find the values for y naught and b. The y naught is the initial value. Okay, now porque y naught is more present at t equals 0. Hey guys, so at the beginning, guys, here where it says at the end of January, there were two cases. So my y naught is going to be 2, because t equals 0 corresponds to the end of January, and in the end of January, there were two cases. So my y naught will be 2. Then it says here, by the end of April, the cases have grown to 128. So let's count from the end of January to the end of April to see how many months have passed. So when t equals 1 corresponds to the end of February, t equals 2 corresponds to the end of March, and t equals 3 corresponds to the end of April. So then at the end of April, there were 128 cases, right? Here, I did it like this, so it can be more visual, but you can go from the t equals 0 to the t equals 3 for the end of April. Now, we use what we know to find b. Okay, we know that my y naught is equal to 2, right? My y naught is equal to 2. This means here, guys, my t is 3 and my y is 128. So going back here, this is like my y, so this will be 128 when the t is 3. So this is from the second point, which is 3, 128. This was plugged into the function. So then we have to solve for b. So my next step is that we have to divide both sides by 2. That will give us 64 equals to b to the third power. At times, here we learned that to solve for b, that we took the cube root of both sides, but the cube root at times cannot be put into the calculator. So that's why we use the exponent power rule. We're going to raise it to the 1/3 power, but we're going to do it for both sides. If we do that, b to the 1/3 power, guys, here we're using the, if you have a power to a power, you multiply the powers. That's why 3 times 1/3 will give us 1. That's how we solve for b. And 64 to the 1/3 power will give us 4. So we found our y naught and we found our b. So now we do is plug into the function, right? So my y naught is 2 and my b is 4. So this is the answer for a, the function that we're looking for. Now for b part, from the end of January to the end of December is going to be 11 months. So for b part, we're going to evaluate f of 11, which means we're going to plug in 11 where the t was on the original function. And now we do is put in the calculator, guys. So this is the result that we should get. About 8,288,608 people will be infected by the end of the year. This is like an estimate, guys, and this is good to use. Well, this is how science uses, like in the real world. And I got this example. This was a time that COVID started. I mean, that was before spring break in 2020. So I got the report from the news, and then I came out with a function so I can show the students how this is related to the real life and what we were doing at that time. Okay, but this is the people infected if there was no intervention. But if you know, guys, right, during COVID, there was an intervention. There were like social distance, 6 feet. There were masks and all that stuff, and also that hand sanitizer to prevent for people to get infected. But this number will be kind of accurate or like an estimate if there was no intervention. Let's move on to number 6. The next thing we're going to cover is solving exponential equations. So this is like a definition or a rule that we're using. If a to the u power equals to a to the v power, then my u must equal to v. In other words, what they mean here, if you have the same basis, then the exponents must equal to each other. Example, I started out with a simple example, like 3 to the x equals 3 to the 5, right? So we have the same base, we can use a rule. So the exponents must equal to each other. So x must equal to 5. Okay, now for this one here, number 6, solve for x. We have 125 to the x power equals to 5 to the 5th power. If we notice, these are not the same base, so we cannot apply the rule yet. So we have to make them the same base. We know that 125 is equal to 5 cubed, right? Because we're trying to match the bases. So we can apply the rule. So now I'm going to plug in 5 cubed for the 125. And we bring down the x, the exponent. Here, guys, on the left side, we're going to apply the exponent power rule, which means when you have a power to a power, you multiply the powers. So the left side becomes 5 to the 3x equals to 5 to the 5th power. Now we have the same base. Now we can apply the rule. So we let the exponents equal to each other. So 3x equals to 5. We divide both sides by 3. And the result will give us x equals to 5 over 3. Okay. And I believe you can always check your work. Okay, but you don't have to check it, but I'm checking it here for you so you know that you can always check your work. And we plug in 5/3 for the x, right? And then if you put that in the calculator, guys, you're going to get the same thing. Okay, so we know that's the correct answer. Okay, let's continue with another example. Let's say we're solving number 7. Solve 4 to the power of x minus 1 equals to 32. Again, here not the same base, so we have to make the 4 and the 32 have the same base. Let's see if 4 to a certain power will give us 32, right? So 4 squared will give us 16, which is not 32. Now let's try 4 cubed. It'll give us 64. It's not 32. That means that we have to find the same base for both of them. So 4 doesn't have 32 doesn't have a base of 4. I mean, as a base for 32. So we have to find the same base for both of them. So we know that 4 equals to 2 squared, and also 32 is equal to 2 to the 5th power. You see now they have the same base. So I'm going to plug in 2 squared for 4, and then bring down the x minus 1. And then we're going to plug in 2 to the 5th power for 32. Now on the left side, we're going to apply the exponential power rule, right? Which will give us 2 to the 2 parentheses x minus 1 equals to 2 to the 5th power. Now they have the same base, which means now we can apply the rule. Now on the left side, we're going to distribute. So that'll give us 2x minus 2 equals to 5. We add 2 to both sides. So 2x equals to 7. Now we divide by 2. So x equals to 7 over 2. And like again, that's the result, and we can always check our work. We're going to plug in 7 over 2 for the x's. 7 over 2 minus 1 will give us 5 over 2 as the exponent. If we put that on the calculator, guys, it's going to give us 32. So we know that 32 equals to 32. So we know that's my answer. Now we're going to be doing writing exponential equations into logarithmic equations and vice versa. So this is how you go from logarithmic to exponential. This is the conversion here and vice versa. So for example, write each logarithmic equation into an exponential equation. So here, guys, we have to know what the a, what the x, and what the y is. If you notice here, guys, the a is going to give us 9. The x will give us 81. And the y is going to give us 2. So now we have to go from logarithmic to exponential. We know that the a is 9, right? The y is 2, and the x is 81. You see there's my a, which is 9, my y is 2, and my x is 81. That's how you go from logarithmic to exponential. Number 9, now we're going to go the other way. Write each exponential equation into a logarithmic equation. They gave us 5 cubed equals to 125. So again, we have to know what the a, right? What the a, what the x, and what the y is. My a will give us 5. My y will be 3. And my x will be 125. Now it's going to be 3 equals to log of base 5 of 125. See, there's my y, 3. My a, my base is 5. And my x is 125. Or at times, it's written the other way. It'll be log of base 5 of 125 equals 3. It's the same result. Now we're going to be graphing logarithmic functions. In order to graph without a calculator, must convert logarithmic equation into an exponential equation. So again, we're going to use a conversion, right? So say the graphing y equals to log of base 2 of x. This will give us, right, my a or my base is 2, my y is just y, and my x is x. Now we're going to do a table, but we're not going to plug in the values for x anymore. We're going to plug them in for y. And this will be much easier because if we're doing for x, then it requires taking the ln, and well, it's more complicated. So it's easier to plug them in for the y value. And again, if we do that, if we plug in negative 2 for y, it's going to give us 1/4. Right? And then if we plug in negative 1, it's going to give us 1/2, and so forth. And I believe we already did this, but for the logarithmic, for the exponential functions, but these values were plugged in for x. In other words, now the y values have the x values from the exponential, and the x values will have the y values for the log because they're inverse of each other. Okay, in other words, here's the result of plugging in all the values. Here's what we get. Right, we plug in 0, we get 1. We plug in 1, we're going to get 2. We plug in 2, we're going to get 4. And we plug in 3, right, we're going to get 8, because if we plug in 3 for the y, we're going to get 8, because 2 to the third power will give us 8. And the graph is the one in red. The one in blue is the exponential, and the one in red is the logarithmic graph. If you see that these are inverse of each other, for 1324, there's not really a topic on inverse, but you do need it for 1314. You see, and here's my graph in blue. In red. Okay. Okay, now, here we have to use some properties of logarithms to expand or condense some of the expressions that they give us. For example, if you have log of base a of xy is equal to log of a of x plus log of a of y. This is called a product rule. And same thing goes with a natural log. The natural log of x times y is equal to the ln of x plus the ln of y. And number 2 here, guys, is called the quotient property. If you have, right, the quotient division, it's going to be subtraction here. It's going to be log of base a of x minus log of base a of y. And same thing with a natural log. The last one is called the power rule. If you notice, the exponent goes to the front. This is called single log, and the right is called expanded. So we're going to be going back and forth. So example, write each expression as a sum or difference of logarithmic with all variables to the first degree. So like I tell my students here, right, we're going to go from single log to expanded log. Here we're going to count how many numbers or variables we have, right? So there's 3 of them. But here we're using just the product property. Okay, so now, so we're going to separate them. I think here I use the wrong term here, but because if we have 3, like we have a coefficient and we have 2 variables, we're going to do 3 separate terms as logs. So that's 1, that's 2, and that's the other one. But if you notice, when they're expanded, there's no exponents. Now we have to apply the power property where the exponents go to the front. You see, the exponent goes to the front. And also for the log of y to the third power, the exponent goes to the front. So this is my result. Let me go back. That's my result. This is called single log. This is called expanded. Again, here are the same properties. There's this one here. Right, so here we have, again, we have all the properties present. We have here the product property, we have the quotient property, and the power property. So there's all 3 properties there. Now, like I tell my students, right, there's 1, 2, there's 3 different variables there. So we're going to put them into three different log terms. this is like the concept here, but at times I show my students the observation, which, at the end, we're going to have three log terms. First, we did the quotient rule, right? So the quotient will be, if we're dividing here, it's subtraction here, right? By using the quotient property. Now we're going to execute the product property, which when you have the times, right, product, we're going to add them. And then finally, we apply the power property, which the exponents go to the front. But I tell my students that they can go from here to the answer. You see, for example, here, right, we have three different variables, the x, y, and the w. That means since this is multiplication, we're going to have addition here. So it's going to be log of x plus plus 2 log of y minus log of w, because when the logs are expanded, there's no exponents. The exponent goes to the front. And I can tell my students that the more that they practice these, the more they can go straight from the term that they give. From the, what's it called? Yeah, from the term, right, to the answer. Right, go straight up from the expression, straight to the answer, just by knowing the properties. And I can tell my students, the more that they work on them on the homework, the better they're going to get at that. That way they can go straight from the expression to the answer. But here I'm showing all the rules. Now we're going to condense them. We're going to put them as a single log. Okay. So for example, here, right, is the other end here, we have the quotient property, right, and also the power property, because now we're going to go the other way. It's expanded. We're going to put in condensed. So first, right, the exponent here is going to go to the top, right? Because, right, this is the exponent, right? The number in front becomes your exponent, it goes to the top. Then we just break down the ln of x plus 3. Now we're going to apply the quotient rule. Put them under one log, so it's going to be x plus 7 squared over x plus 3. And I keep showing my students that they can go from the expression to the answer. You see how? We know that if you're going to go as a single log, right, there should be no numbers in the front, right? You see, because a single log, they don't have nothing in front, no numbers in front. So we know that's my exponent, so we raise it, that goes up. And then when we have subtraction, it's going to be division. And then all you do is put them as a single log or a single natural log. Now this is solving logarithmic equations, and again, we have to use some of the properties. For example, here, remember guys, when we try to find the same base, well, eventually there's another way to get the answer. Okay, we're going to take the ln on both sides. You can bring down right, to bring down the exponent, we're going to take the ln. That will always bring the exponent down, right? Because we're applying the property here. To bring the exponent down, we take the ln and the exponent goes to the front. That's what's going to happen here. You see, the exponent goes to the front by using the property here, the power property. Now we're going to divide both sides by the ln of 6. We just put in the calculator. It's going to give us something like 2.386852807. But most of the times I want you to round it up to 4 places. It's going to be 2.3869. Hey guys, I put here very important, guys. Hey guys, the ln of a number is actually a value. You cannot separate the ln from the number. For example, here, you cannot separate the ln from the 72. This is a value. This is together. Okay, so make sure that you understand that. Now we're using another property here. If you have log of base a of u equals to log of base a of v, then u must equal to v. Okay, in order to apply this property, you have to have a single log on both sides of the equal sign. You see, for example, the right side is not as a single log. So we're going to apply the properties, right? Remember, if it was subtraction, it's going to be division. Now, by applying the properties, right, then the x must equal to the x plus 3 over x minus 1. That's by applying the property here or the rule. Now here we can cross multiply, or we can multiply both sides by x minus 1. It all depends how you actually solve these problems. If you cross multiply, right, there's like a 1 here on the bottom of the x. So it'll be x times x minus 1 times x plus 3. Or you can say, I want to multiply both sides by the denominator, which is x minus 1. If you do that, this is my result. So it's going to give us x squared minus x plus 3. So now we have to set it equal to 0. Okay, so we're going to subtract negative x minus x and negative 3 to both sides. It's going to give us x squared minus 2x minus 3 equals 0. Now we got a factor. It will give us x minus 3 times x plus 1 equals 0. So x equals to 3 and x equals to negative 1. Okay. Now the logs cannot be negative. Okay. On the next, we're going to check our answers on the next slide, but the logs cannot be negative. You see, we plug in a negative 1 there. If you put in the calculator, log of negative 1 is going to be undefined or error. That means the logs cannot be negative. Okay. Now if we plug in 3, right? So let's do it. So let's check our work. So it's going to give us log of 6 minus log of 2. You can actually put that in the calculator if you want. This is a result, or you can do it by hand by using the properties. Isn't this on the right side the quotient property? Because if it's minus, you put it as a single log, and it's going to be division. And 6 divided by 2 is 3, so we got a log of 3 on both sides. That's how we can check our work. Now here's another one here, okay? By using this property here, if you have base a to the log of the same base, then the answer will be for the US. Okay, example. We want to solve for x. We don't want the log of 4 there. So the base of the log is 4. So we're going to raise, so both expressions becomes my exponent, right? We're going to put a big 4. This becomes your exponent, but we do it to both sides. You see, now we're applying the property here above. So the left side will just be 5x plus 6. On the right side, 4 squared will give us 16. Now since we're solving for x, we're going to subtract 6 to both sides. It's going to give us 5x equals 10. Now we divide by 5, and the answer is 2. And you can always, again, check your solution. We're going to plug in 2 for the x. So it's going to give us 16, right? And the answer, if you apply the property by change of base, it's going to give us 2 on the left side and 2 on the right side. But if you recall, when I did this presentation for that week, here's how you read it. You ask yourself, 4 to what power gives me 16? That's why the answer is 2, because 4 squared is 16. That's why this on the left side becomes 2. Now comes the problems for chapter 5. This is number 17. This is simple interest. It says Gabriel invested his summer earnings of $3,000 in a savings account for college. The account pays 1.5% simple interest. What will be the value of this account after 2 years? And how much interest did he earn? So this is a formula to find the future value of simple interest. Okay. So I tell my students to always put all the variables here, and then we're going to extract the info from the problem. Okay. So here right away we know that we're looking for the future value, right? Because it says here what will be the value of the account after 2 years. So that's in the future. So we're looking for the future value. So the 3,000 is what you invested at the moment right now. Right now. My R, which is the interest, will be 1.5%, which will give us 0.015. And my T has to be in years, right? And time is also in years, so it's 2. So all we do is plug into the formula, use the calculator, and that's my result. Now to find the interest, right, it says how much interest did he earn? So the 3,000 he invested in an account, right, for college. So how much interest did he earn in 2 years? So we subtract the the future value, right? The $3,090 minus the initial investment, which was 3,000. That's why the answer is 90. So Gabriel earned after the account. Gabriel had 3,090 in the account, and Gabriel earned $90 in interest. That's the answer for 17. Now for 18, it's called compound interest. This is a formula, right? But it's better to use this one here at the bottom, because my I is the same thing as R divided by M, and the N is the same thing as M times T. Here's what everything means. FV stands for future value. PV stands for present value. The R stands for the interest rate, which is always in decimal, but you have to convert it to a. I mean, it's in a percentage. You have to convert it to a decimal. The M is the number of compounding periods per year. T is the number of years. The I is R divided by M, which is the interest rate per period. And the N is M times T, which is the total number of compound periods. And here are the key words for compound. For example, if the problem states yearly or annually, M is equal to 1. If it's semi-annually or bi-yearly, M is equal to 2. If it says quarterly, my M is 4. Monthly, my M is 12. Weekly, it'll be 52. Daily, it'll be 365 or 360, depends what the book wants you to use. And if it's continuous, it's a different formula. Okay. And these type of problems, compound interest can be used to invest a certain amount of money without depositing additional money. That's what this is used. These type of problems are used for. For example, number 18. Okay, they say you deposit $9,000 in an account at your bank that pays 2.5 interest semi-annually. How much money will be in the account after 10 years? This situation is, say that you had that much money, right, and you want to open a compound interest account. So let's see how much money you will have after 10 years, and then how much interest did you earn. So again, we're going to use the second formula because it's easier to put into calculator. So there are 7 things that you got to find: the future value, present value, my interest rate, my M, which is a compounded per period, my T, my I, and my N. So here, guys, right, we're looking for the future value, right, because it states here how much money will be in your account after 10 years. So that's in the future. My present value will be 9,000. My interest rate will be 2.5%. Converted to a decimal will give us 0.025. My M will be compounded semi-annually, which will give us 2. My T is in years, so it's 10. My I is R divided by M, 0.025 divided by 2, which will give us 0.0125. And my N will give us M times T will be 2 times 10, will give us 20. Now let's plug everything in the calculator, right? You put it in the calculator just the way it is, that's my result, which will give us $11,538.34. Okay, now, how much interest did you earn? Okay, so we subtract what you invested minus what you got in the future, which was the 11,000 after 10 years. Right, so if we do that operation, it's going to give us $2,538.34. So this is how much interest you can earn and under this situation here in 10 years. Now, number 19, this is another one. Okay, this is different. This is future value of an ordinary annuity. Here's the problem here. At the end of each quarter, a 50-year-old woman puts $1,200 in a retirement account that pays 7.2% compounded quarterly. When she reaches 60, what will be the value in the account? And how much interest will she earn? Okay, now, so again, this requires a different formula, but there's 7 things that you got to know. Here we're looking for the future value, right? Because when she reaches 60, what will be in the account? So we're looking for the future value. So the payments that she's putting every quarter is $1,200. The interest rate is 7.2%. which will give us 0.072. Compounded quarterly, so m is equal to 4. The time, and guys, here for students begin to make mistakes, because just because they see the 50 and the 60 there, they think those numbers have to go in here somewhere. But the problem is that when this woman, right, when she was 50 is when she started the account, the annuity account, and then she wants to know how much money she will have when she's 60. So we subtract 60 minus 50 will give us 10. That's the time in years. Now the I will be R 0.072 divided by 4, which will give us 0.018. The N is M times T, which will be 4 times 10, will give us 40. So we do is plug in the formula. And I'm going to show you here, I'm going to show you how to use it without clearing or stopping one steady flow until you reach the answer. Because at times students, they don't know how to plug it in, so I want to show you step by step. So the first thing that you're going to enter is a numerator. The parentheses 1 plus 0.018, close it to the 40th power minus 1. And this is the result, 1.0413201138. Then you're going to hit the division key, right? And he's going to show you, okay, what's taking place. I'm going to hit the division key. Why? Because we're dividing the answer that we got in the numerator by 0.18. Then we're going to enter 0.018. And this is what we should see. 57.85111.879. Now we're going to hit the multiplication key because we're going to multiply that by 1200. And this is a result, $69,421.34. So that's how much the woman will have after 10 years. Okay, now how much interest did she earn? So why do we do that? She's making payments of $1,200 right every quarter for 10 years. So there was 40 payments, or 40 payments that she made. So we multiply the payments times the number of payments. So 40 payments times 1,200, which gave us 48,000. So that's how much money she actually came out of her pocket. So the rest is going to be an interest that she earned. So when we find it, we take the future value of what she earned in those 10 years minus what she paid. Actually, what came out of her pocket. So it gave us $21,421.34. That's how much the woman will have after 10 years. And I think that's not bad, right? If she did it right, so in 10 years, she made 21,000. So she made like 2,000 per year, a little bit over 2,000 per year, which is extra money there. Now, number 20, which is the last one. This is one of my favorite ones because this is where I show my students how to, when you purchase a car, when you purchase a house, what you have to, how can you get your monthly payments? Okay, so that's what we're doing here on number 20. It says here you want to purchase a house for $325,000 with a 30-year fixed rate at 3.9%. What are your monthly payments and how much interest did you end up paying? So again here, guys, there's a different formula. There's 17 that you gotta search for, right? So here, guys, we're looking for the payments, right? So we're looking for the PMT. The present value, hey guys, this means that this is the money that you're gonna borrow from the bank to purchase a house. So 325,000. The R is the interest rate, which would be 3.9%, which will give us 0.039. Because most of the times the compounded period is mostly monthly because it's always you're paying monthly payments for the house. So the M will be 12. The time is 30. So the I will be R divided by M will give us 0.039 divided by 12 will give us something like 0.00325. The N is M times 10, which will be 12 times 30 will give us 360. So we'll plug into the formula. Right, and again, I'm going to show you how to use a calculator in one steady flow. So first, we're going to enter the numerator, which would be 1 minus parentheses 1 plus 0.00325, close parentheses to the power of negative 360. And this is what you should see on your screen on the calculator. After that, you're going to press the division key, right? Because we're going to be dividing the answer by 0.00325. So once you press the division key on your calculator, this is what you see. It means the answer divided by. So the answer was 0.689 something, right? Now we're going to enter the 0.00325. Once you enter that, it gives us 212.0134431. Now we're going to hit the inverse key. And like I showed on the PowerPoint from the week before, to find the payment, right? Right? Because here, guys, right? Once we get what's in the right side, we divide both sides by that, right? But for that, you have to stop the calculator and clear it and enter the numbers again. But if you do it this way that I'm showing you, you can do it in one steady flow. So how do you divide what we got on the right? How can we use that? So we use the inverse key. That key multiplies by the reciprocal of what we got on the right. So all you do is hit the inverse key, and then you enter the number on the left, which was at 325,000. So this is my result that you should see. So the payment was for $1,532.92. That's how much your monthly payments will be. Now, how much money did you end up paying for the house? This is the answer for the first part, but how much interest did you end up paying? So we multiply the number of payments, which were 360, we multiply by the payment. So 360 times $1,532.92 will give us $551,851.20. This is what you end up paying for the house in 30 years. Okay, now, so how much was interest? You subtract what you borrowed from the bank from the total value of all the payments, right? And it's going to give us $226,851.20. So you end up paying like over $250,000 in interest. Now, how can you eliminate some of the interest here that you don't want to pay that much interest? What you do is you pay more money every month into the principal. You tell the bank that the extra money that you're paying is for the principal. This way, it goes straight to the principal, and this way you can pay the house in a quicker time, and also pay less interest. I guess I believe this is it for the PowerPoint, guys, for this presentation. I hope you enjoyed it. Most of these questions I do put them in the exam for my students. Not all of them, but for sure the last 4, and I choose 6 from the other problems there. But hopefully your instructor will give you some of these. That way you'll be able to actually do them. Because I want to thank you guys for coming to today's Friday Happy Hour. Thank you, and have a wonderful weekend.